Hello everyone, welcome back to our Python workshop. I'm Chi, and today we will start the day 2 part of our workshop. So, after getting familiar with Python basics, we're now diving into the core libraries of data science in Python. And the first fundamental package we will learn today is NumPy. So, as everyone knows, data science is a field that's been getting a lot of attention lately, but actually, data science isn't a brand new field. It's more like a mix of things we already familiar with, such as statistic programming and specialized knowledge. For us, that specialized part is health and environmental science. Now let's take a look at this Venn diagram. It gives us a nice visual of how data science comes together. So where those circles overlap in the middle, as you can see, that's the spot where coding skills, math knowledge, and the subject expertise all meet up. Now you may be wondering why we're using Python for all of this. Well, actually Python comes with this great toolkit, what we call an ecosystem, that makes data work much easier. And we will be getting our hands on some of those tools like NumPy, Pandas, Matplotlib, and SciPy in the coming sessions. But for now, let's first take a quick example with this image. It might not look like it, but an image is really just a grid of numbers showing how bright each pixel is. And when you think about it in this way, you can see why we analyze and change images by just tweaking these numbers, and how NumPy, those numerical metric, actually represents a common raster image in Python. So the agenda for today is, first we're going to talk about NumPy arrays and what are the common array manipulation and math we can do, and finally how we should commonly handle missing data in NumPy. And as we go through these topics, you'll see how NumPy helps us handle the big complex data sets we often run into with climate and environmental research. So first, what is NumPy and why it is such a big deal? Well, NumPy stands for Numerical Python, and it's basically the backbone of scientific computing in Python. It's very good at handling array-based datasets, and in fact, most Python packages for data work are built on top of NumPy arrays. So in this session, we're going to cover the basics. So how to create arrays, how to use NumPy functions, and how to do some array math. But keep in mind, we're just scratching the surface here. NumPy has tons of operations, functions, and modules. And if you want to dig deeper, the NumPy documentation is your best friend, and I would highly recommend you to check it there. But before we jump into NumPy itself, let's take a quick detour and talk about importing libraries in Python. So in Python, most of the packages we use, including NumPy, are developed by third parties. But Python also comes with some built-in packages that are super useful. So here, in this table is some of common modules that we often use in Python. OS standing for operating systems, and this you usually need to import this when you are reading files or getting the file paths. And also math provide access to basic mathematic functions. Random just implements pseudo numbers generators for various distribution, and datetime they can provide a precise date and times for the data. So another important question is how to import these modules. The basic syntax is showing here, so you can use import and then just type the module name, then you can import the entire module. But sometimes if you only want to access a specific part, you can use the from module import identifier to import a certain class of the module. And all modules and packages either used in a single code file or used in a program should be imported at the beginning of the program. And many packages have also standard abbreviations. So for example, datetime you usually import it as dt because that's less word and it's easy for us to coding. And the standard syntax for importing NumPy is importing NumPy as np. If we run this code, and you can see that this code has already been executed, now we can use the NumPy module. So first, let's take a look at NumPy arrays. So these are fundamental to working with NumPy. Specifically, NumPy uses something called an ND array, which is standing for multi-dimensional array. And it is a container that can hold multiple items, but with important rules. That is, all the items must be the same type and size. And we call this property homogeneous in this case. And array can come in different dimensions. Typically, you have one-dimension arrays like a single column. Two-dimensional arrays are like grid with rows and columns. So you can imagine this as a single band image. And yes, you can even have three or more dimensional arrays, which are essentially arrays within arrays. Now first, let's take a look at how we can create these arrays. And one way is to use a function called np.array. It's pretty straightforward. You just feed it with a list. And here, we're creating a NumPy array by inputting a list of numbers. And if we run this, we can see that we get a single array. Now, here is something cool about NumPy arrays. They are smarter than usual Python list. So if you mix different types of numbers, NumPy will try to find a common type that works for all of them. And in this case, it's upcasting all the elements. So for instance, here we have a list of numbers with integers and float. And if you're trying to create a NumPy array from this, what NumPy will do is it will convert everything to float. So now you can see that 9 has been converted to 9.0 and 4 also is now a float number. And by the way, we can also check the shape of our array using the dot shape function. And you can just add dot shape to the end of the last array we created. And now you can see that this is a one-dimensional array. Here you can see 5 comma. So in the above example, what we have created is called a one-dimensional array. And by default, elements in the one-dimensional array are cast as rows in the number. So what you see here is a column vector. But if, however, we want a row vector instead, we could use a double brackets to create an array. If we run this code, and if we put the shape again, and now what we see that now these new NumPy array that are wrapped by the double brackets actually has 1 row and 5 columns. And why we have this discrepancy is because NumPy treats the inner elements or list as rows. And this idea of inner elements being treated as rows becomes really clear when we create multi-dimensional arrays. We can check this out. So if we run this code and check the shape, we can see that we got 3 rows and 4 columns. And as you can see that the inner list here, the first list, 3201, is understood by NumPy as a row, and that's why here we have 3 rows and 4 columns. Alright, now let's talk about some cool ways to create arrays using NumPy functions. Sometimes it's more efficient to build arrays from scratch rather than converting from list. So first, we have the NumPy arrange function, and this is super handy for creating arrays with evenly spaced value. It's pretty flexible. You can use it with 1, 2, or 3 parameters to specify the start, stop, and step values. So this is pretty similar to the list range function. And if you run, this will just give you an array starting from 0 to 6. and this has 7 integers in this case. And if you want a float instead, we can add a decimal point. So now what this code giving us is the integer number starting from 1 to 12. Sorry, float number. And to make it more complicated, you can also set a step size. So for instance, NumPy arrange starting from 0 to 21, and you can use a step of 2.5, and this will give you values from 0 to 20 incremented by 2.5 each time. And similarly, we have another useful function, which is NumPy length space, and this one is a bit different. So instead of specifying a step size, you tell NumPy how many numbers you want, and it spaces them evenly over your given interval. So what this code will do is that it will create an array of 5 evenly spaced values between 0 and 1. So 0 is the start and 1 is the end. And now we can see that this creates 5 intervals. So it's 0, 0.25 until 1. And here is a little tip. So unlike NumPy arrange, NumPy length space includes the stop value by default. And if you don't want that, you can add endpoint equal false as an argument in your function. And one more thing, if you need non-integer steps like 0.25, this function NumPy length space is usually the way to go because it handles these cases more precisely than NumPy arrange. And additionally, there are some really useful NumPy functions for creating arrays with specific values. So first, we got NumPy 0, and this is quite straightforward. It just creates an array full of zeros. So if we put NumPy 0, 10, this will just give us a one-dimensional array of 10 zeros. And if we pass a tuple like 4 by 3, and this will create a 4 by 3 arrays filled with zeros. Now, if you don't want zeros and want some other numbers, for example, like ones, then you can use the NumPy ones function. It works exactly the same way, but just instead of giving you 0, it will give you 1. And if you want an array filled with a specific number, for example, pi, and you can use the NumPy full function. And what you need to do is you just need to add another parameter after the size of the array you want to create. And then in this case, you just add a 3.14 after the arrow size, and then this will return you an array filled with pi. Moreover, you also can use the NumPy random.ran function to create arrays filled with random numbers between 0 and 1. And this is very useful for sampling and modeling. So as you can see here, we just created some random number, a 4 by 3 array of random number between 0 and 1. And last but not least, we can use the NumPy I function. It creates an identity matrix. So if you run this, you can see that all the diagonal becomes 1 and the rest is 0. Lastly, there is a pro tip. All these functions have an option of data type parameters, and these will allow you specify the data type of the array. So for example, if instead of creating a float, if you want to create an integer, so you can just add a parameter dtype equal to integer, and then all the ones you get will become an integer. Alright, now that we know how to create arrays, let's try to learn how to manipulate them. This is where things getting really interesting. You know, almost all data manipulation in Python involves NumPy arrays in some way. Even other tools like pandas are built on top of NumPy. So, while some of these operations might seem very simple, they're actually super important for understanding more complex data manipulation in Python. First, let's talk about array attributes. These are like the array's ID card or properties. They tell us important information about the array's size, shape, and type. And below this table are 4 main attributes that we will use a lot when we are doing data science in Python. So the first one is undim, and this tells you the number of array dimensions. And shape, this gives us a tuple showing the size of each dimensions. So rows, columns, and dot size will tell us the total number of elements in the NumPy array. And finally, the D type is just the data type of the array elements. Now let's see this in action. So first, we'll create a random 2D array called A and explore its attribute. So first, let's use the random.rand functions that we just learned to create a 4x7 array. And as you can see, now we have a two-dimensional NumPy array A. And if we want to check the array dimension, and this will let us know that, okay, this is a 2D array, which means that this array has 2 dimensions. And if we want to check the shape, we will know that it's 4 rows, 7 columns, and then the size will return us 28. This is because 4 times 7 is 28, so we have in total 28 elements. And finally, the D type will be float 64 because we're creating a floating point numbers from the random function. And now here is a little exercise for you. So you can try to create 2 arrays from the list A0914 and make one a column vector and one a row vector. And then use the undim and shape to see the difference between them. And remember, for a column vector, you use a single brackets, but for a row vector, you use double brackets. And now you can pause the video and try to exercise this. Okay, moving on. Now let's talk about indexing and slicing in NumPy arrays. So if you're familiar with Python list, you'll find this pretty similar, but with some extra cool features for multi-dimensional arrays. Again, let's start simple. Say we have a one-dimensional array called x1, and now we'll initialize them from a list A0914. To get a specific value, we can, similarly to a list, we can use a square bracket with the index. In this case, the x1 square bracket 1 will return the value in position 1. And that will give us actually the second element because remember again, Python starts counting at 0. And now you can see that we have the number 0, which is the second element returned from the x1 array. Now here is where it gets more interesting. So with multi-dimensional arrays, we can use a tuple of indices to pinpoint exactly which element we want. So first, let's create a 2D array x2, and in this case, we have 3 rows and 4 columns. And let's say if we want the elements that in the second row and third column, then we just put square bracket 1 and 2. And remember again, the 1 and 2 is because Python started indexing from 0. And this will give us number 8. And if you go back to check, you can see that number 8 is indeed on the second row and starting from left to right, the third column. If we want a whole row, this is very easy. So you can just use one index. In this case, if we want the entire second row, we can just put x2 bracket 1, and then this will give us the second array. Now moving on, let's talk about slicing. And this is how we can subset parts of our array. And the syntax is also very similar to a list. So you have the start, stop, and step. So for example, if we are slicing a one-dimensional array x1, say if we want the first 4 elements, and then we can use x104 to slicing. And if we are slicing a 2-dimensional array, the syntax for slicing separated by a comma. So the first part, you're gonna specify how you wanna slice the row, column, the row. And then the second part, you're gonna specify how you wanna slice by column. So Let's break this down with some example. In the first code, what this will do, x2, and we leave the first part empty, and then we just put 2 in the second part. So what actually this means is that this will return us all rows, and the 2 after the comma means that the third column, remember again, we start counting at 0. So what this code is actually, we are trying to ask NumPy to give us all the rows, but only the third column from the array. And this will give us 0, 8, 1. And if we go back, we can see that here we're only slicing the third column. And again, now this will return us the first two rows, and also the first two column. So let's break it down. These before the comma means that from the start all the way until, but not including index 2. And this is the same. If we run this, we'll have the first two rows and also the first two columns, 3, 2, 9, 1, and exactly. And now let's move on to this. So for this example, this will return us all rows and every other column. Here is what it do. So again, the column before the comma means that all rows, and after the comma, the double column means that start at the beginning, go to the end. And the final parameter, of 2 here means that in this case, we're slicing them using a step of 2. So this code will return us all the rows, but only every other column. All right, now let's talk about array reduction in Python. So array reduction refers to the computation of summary statistic on an array. That is reducing an array to a single aggregate value. So for example, such as means, minimum, maximum, standard error. So common statistic matrix from a data set. That's how you can understand it. Now again, we're creating a new two-dimensional array called x2. And if we want to calculate the sum, we just put x2.sum, and this will return us the sum of the elements. And if we want to find the maximum value, we can see that it is 9. Similarly, the minimum value will be 0 in this case. Also, it can check the mean and the standard. Now, here is where it gets really interesting. So all of these methods can take as an access argument, which will let us apply this operation to specific dimensions in our array. So instead of running this summary statistic for the whole column, you can specify along which dimension you want to perform this statistic. So in Python, access 0 always refers to the rows of an array, while access 1 refers to column. If we want to calculate the mean of each row, we can just put x2.mean and add access equals to 1. This means that the mean function here will be calculated across column, and that will give us the mean of each rows. And if we put x2.max, and now we put access at 0, this will give us the maximum value of each column, and that's 9287. If we go back, we can actually see that the maximum value of first column is 9, second 2, 8, 7. And here is something about Python that's good to know. So functions and methods are basically the same thing. The main difference is that methods are attached to objects, while functions can be called on their own. So for each of these reduction methods we have talked about, there is also a corresponding function. So you could use, for example, numpy.mean instead of x2.mean if you want to calculate the mean. And in example, that would be x2.mean, and then this will give us 3.5. But we could also use numpy.mean, and then we put x2 on it. And this is how you can also get the mean by a function. Now let's move on to reshaping, resizing, and rearranging arrays. These are also super useful tools when you are working with data and sometimes need to change or modify the structure of your array. So again, let's begin simple. Now we're initializing a 1D array with 16 elements and we name it A. So we have an array A starting from 1 to 16 and they are all floating numbers. Say if we want to reshape them into a 4x4 array, we can just use the reshape function, and then here in this tuple we just pass the shape, the array size. We just modified our one-dimensional array A into a 4x4 array B. But there are a couple of important things to remember about reshaped. The first thing is that the size of the array has to stay the same, meaning that you cannot reshape a 16-element array into a 5x5 array because the size of them just doesn't match. And secondly, here is the tricky part. So when you use the reshape, you're not actually creating a new array, but instead B is what we call a view of A. And why do this matters? Well, if we run this code, if we're trying to reset the value, for example, in the third element, in the third row and third element, in this case, 11, if we were trying to change it into 0, and now we can see it was indeed changed into 0 in B. And now if we print A again, we can see that the number after 10, which was originally 11, now has also been converted into 0. So next time, if you're working with array data and want to change its shape, remember that if you're using the reshape function, you are creating a view, not a copy. And if you don't want to change the original structure of your array, always remember to create a copy. And now let's talk about another way to restructure your array dataset. So NumPy has this function called resize, and this method is different from reshape in a key way because it operates directly on the original array and it can change the total number of the elements. Here is how we can use it. So first, let's start with a 2x3 array called A. And now if we want to make this array smaller, first, as we remember that this is an in-place operation, so we can first create a copy of the original array. In this case, we call it smaller, and then we use the resize to reshape it into a 2x2 dimensional array. And if we print the smaller array, we can see that now we only have 1, 2, 3, 4. And we can see that the last 2 elements was dropped. On another scenario, maybe we want to make our original array bigger. And similarly, in this case, we're first creating a copy and we're using the resize function to reshape our 2x3 array to a 6x3 array. And in this case, the resize function expands our 2x3 array to a 6x6 array. The original elements stay in place and the new space are filled with zeros. And now, if we print A again, we can see that all the elements in A has been untouched. So notice that in both cases, we're using a copy function before resizing, and this is crucial. If we didn't do this and apply resize directly to A, we will be changing our original data. And by creating a copy first, we can protect our original array. And another thing is that the resize method is particularly useful when you need to add or remove data from your array. So unlike reshape, which just reorganize existing elements, resize can actually change the amount of data or elements in our array. And now let's explore how to rearrange elements in a NumPy array. There are several useful methods for these purposes. First, we have the ndArray transpose method, or simply ndArray.t. What this function do is just it will transpose the array, switching the rows and the column. So now let's look at this example. We're creating a new 4x5 array of x, and if we want to transpose the array, we just put x.t, and now we can see that the rows has become the columns, and then the columns has become the rows. And secondly, we have more other functions to rearrange the order of the elements. We can use the flip function. This will just simply reverse the order of all the elements. It's like turning the entire array upside down and backwards. And now we can see that the last elements now become the first element, and then the second last now become the second one, and so on. And if we want to have more subtle operation, we can use, for example, the flip up. This will flip only the array up and down, which means that reverse the order of the rows. And then we can see that now the last rows has become, in this case, the first row. And then the flip LR will flip the array left and right, which means that we are reversing the order of the columns. And now we can see that originally the last column 5094 has now become the first column. And also the other parameter you can adjust is the axis argument. The NumPy flip function actually mimics the NumPy flip up and also flip LR functions. And if you want to flip the array over the row axis, you can put axis equals to 0. And if you only want to flip the column axis, then you can set the axis equals to 1. And so far, we have considered array manipulations that operates on a single array. But in Python, we will actually encounter many scenarios in which it's necessary to combine multiple arrays into one, or slip a single array into two or more separate objects. So to join two arrays, there is one function we can use, that is concatenation. And it refers to the process of joining multiple objects end to end. And the most common way of concatenating arrays in Python, in NumPy, is using the NumPy.concatenate function, which takes a tuple of arrays. So in this case, first we are initializing a 3x3 array of x, and then we have another two-dimensional 1 row 3 column array of y. And if we use the concatenate function, what this will do, it will just append 2a6 to the 3x3 array of x. And now you can see on the new array from the concatenate function we got now has 4 rows and 3 columns. And note that by default, the concatenate operates along the row axis. And if you want to concatenate along the column axis, again, we need to specify the axis parameter as in our argument. So if we're trying to concatenate here along the column, we got an arrow, and this is because we were trying to concatenate an array with 1 row to an array with 3 rows. So for the concatenate function to work, first thing is that the dimensions must match. So first, we must transpose the y before adding it to x as a column. If we first transpose the y, and if we run it again, now we can see that the y of 2a6 has been concatenated and as the 4th column in this case. And equivalently, we could use the numpy.vstack or numpy.edgestack function to concatenate directly along the row or horizontals respectively. So the vstack stands for vertical stacked, and then this will just, similarly to the concatenate, it will just appending new arrays along the rows. Then the horizontal stack, again, similarly to when we are specifying axis equal to 1 before, this will just append them along the columns. In contrast, the splitting function will allow you to break down a single array into multiple arrays, and splitting is implemented with numpy.slipped, and again, similarly, numpy.verticalSlip or numpy.horizontalSlip function. And in this example, first we're creating a 4x3 array named z. And now if we want to slip z into two arrays at row 1, what this will do is just it will split z into two arrays, and it will take the first row out, and then the rest from the second until the last row will become the other separated array. Or if we can also use the vsplit function, and again recall this will do the splitting by rows. And in another case, if we want to split them into two arrays by column at the column 1, then we can use the horizontal split function. And in this case, first column has been taken out, and then the second and third has become the new array. And multiple indices can be passed to the split function and related functions, with n indices resulting in n+1 subarrays. Now, moving on. One of the key advantages of NumPy is actually the ability to perform vectorized operations using universal functions, or short ufuncs, which will directly perform element-wise operations on arrays very efficiently. For example, if we have a very large list of data and we want to perform some mathematical operations on all of the data elements, and now in the following example, I'm going to show you the advantage of why when we are doing very big scale data analysis, we would often go for NumPy array instead of using a list. So there are two ways of creating or to store data. So the first one is to create a list. In this case, we're creating integers from 1 to 10,000. If we run this code, first A is a list of the first 10,000 integers, but we can also create a NumPy array, and this will again store the first 10,000 intervals. And now, if we want to do some math on these two variables we just created, for example, we're trying to multiply each element by 2, and if we are operating this on the list object, we can typically use a for loop. And for a NumPy array, we can just use what we call a universal function. And in this case, just multiply by 2. And what this %time_it module will do, it will just tell you or return how much time it will take for the calculation. And now if we run this code, this will probably take a while. Let's just wait a bit. But the idea is just to prove that, okay, so now we got the first output. We can see that it took around 866 microseconds to run every calculation per loop. And now let's just wait for the second one. And we can see that it's only taking 18.6 microseconds as compared to running a for loop using list. And this can prove how efficient it is to use NumPy for mathematical calculation in Python. And those universal functions are actually very straightforward to use because they are simply relying on Python's native operators. So here, if we create a new variable of x, which is a 2x4 array of float, if we try to do some math, for example, x plus 12, and this will just add 12 for all the elements. We can also do exponentations. This will just calculate the squares. And even we can do some more complicated mathematical operations. So essentially, these arithmetic operators act as wrappers, which in a sense are the shortcuts around specific built-in NumPy functions. And for example, the plus operator is a convenient shortcut for the NumPy.add function. And again, if we perform this again, this will actually execute the same operations in the system. And here is just a table of different arithmetic functions that we can use in NumPy arrays. And you can see basically all the common mathematical operations can be done using Python. Also, it provides log arithmetic functions and also trigonometric functions. And you can also use NumPy to access some common mathematical constant, for example, the e and also pi. And finally, let's move on to the array-to-array math. And so far, we have only considered operations between a single array and an integer. But often, it is necessary to perform mathematical operations over multiple arrays. And much like how NumPy handles single array operations, And array-to-array math in NumPy also use the uniform functions to perform element-wise calculations. So for example, now we are creating two array of x and y, which has the same size. And if we want to calculate the sum of them, we just simply use x plus y. And if we want to do a division, there you go, you also got the result. But this is a very ideal case because x and y has the same dimension. And for arrays whose dimension does not exactly match, NumPy will actually try to what we call broadcasting the arrays so that their size or their dimension match when they're performing the mathematical function. And here is just a graphic example. So in the first case, we can see that we have 4 rows, 3 columns, 2 arrays, and the plus will just simply sum the elements by elements. But what if we have first 4 rows by 3 columns, but only like 1 row by 3 columns? So what Python or what NumPy will do, it will just duplicate those rows to match the size. In this case, they will duplicate the rows to 4 rows and to run the math again. And similarly, if we have, for example, a single column of 4 rows and then a single rows of 3 columns, and NumPy will just broadcast them into 4 by 3 dimension and still return the same result. So if we see this example, a plus b will correspond to the first calculation in this case, and a plus c, as we can see that c is only 2 rows and 1 column. What this will do is that it will broadcast this into 4 columns, and you can even multiply them. And so finally, a very important thing is how we handle missing data in our NumPy array. Because in most real-world cases, especially, for example, environmental dataset or health datasets, we often have, or one common challenge is the data gaps. Because data can be missing for any number of reasons. So we need to know how to deal with missing data. And commonly, missing data should not just be replaced with zeros because 0 can be a valid value for many datasets, for example, temperature, precipitation. And instead, it is common practice to fill all missing data with a constant called none values. And none stands for not a number, and it's implemented in Python as numpy.none. And nones are handled differently by different packages. But in NumPy, all computations involving non-values will return a none. And in this case, we're creating a data array which has on the second rows and the last column we have a none array. And if we just simply calculate the mean, we will see that NumPy will return us a none value. And in this case, this is because we have a null data. And if we use the alternative function of numpy.nomean, this will ignore all the nones in our datasets, and the nomean will only taking into account of the valid numbers in our array. And similarly, you can use the nomean and also nonmax and nonsum. These are similar to the regular uniform functions that we talked about, but allow for computation of arrays containing non-values. So to wrap up, I hope you enjoyed our session today. I know this is a lot of information, so try to practice all the code and ask us questions if you have. And as always, I will encourage you to explore the official documentation of NumPy for more comprehensive information of all the functions, methods, and any other practice that you can use. And in our next session, we're going to explore one of the data science favorite libraries, that is pandas.